So let's begin. This is the 2018 paper I've selected from November, right? It is for 1 hour and 15 minutes, right? So we'll get on with the first question. Question number one, element X can undergo the following physical changes. We see this element X, which is turning into three different forms, right? We have liquid, gaseous, and solid. Give the scientific names of each of the numbered physical changes, right?
First
So
one is boiling.
first one is boiling. Sorry, first one is number one. Yes, first solid to liquid. That would be melting. Very good, right? That's going to be melting. Next, number two, condensation. Very good. Next, number three, from liquid to solid. Freezing. Very good. Sublimation. Okay, very good. Okay, next one. Explain why the changes shown are physical changes. Why these are physical changes? They're physically visible. No, that's not how we're going to narrate this. Just a moment. Let me turn on this. Okay. No, 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 no. That's not how we define it. No, 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 no. Why they're calling them as physical changes, right? Why this is not a chemical change. Exactly. But how do we define a chemical change? What is a chemical change? Think of this. What is a chemical change? Two things react, right? One thing or uh, something new is forming, right? New product or new product, something new forming. Could be either way. So we can say that this is a physical change because it's X, X, and X, right? So no new substance formed, right? During those changes, right? Or there's no change in the substance, it's still X, right? So you will have to narrate it like this. What is a physical change? It's a change, since we're dealing in chemistry, so your language has to be ascertained in a way that you reinforce that there is no chemical change happening here, right? And how can we say that? There's no new product formed, no new substance formed up, right? Clarified? A simple answer, but a very specific answer is needed here. Okay. One difference between boiling and evaporation is the rate at which the processes occur. State one other difference between boiling and evaporation. Hmm. Difference. Yes. Danya, any answer? Hmm. Very good. Boiling occurs at specific temperature while very good, right? Within the liquid range, right? Evaporating occurs at any temperature in liquid range, right? Perfect. Perfect answer. Okay, next one. Describe the separation, arrangement, and motion of particles of element X in solid state. Solid. Separation. In solid state, how they're separated, like how they're arranged in general. Let's go with arrangement first, then you'll understand what separation means. How is their motion? Let's start with motion. That's easiest to explain. Vibrate, right? Vibration, right? Or vibrate, that's motion. Arrangement, that would be separation now. tightly packed, right? Tightly packed or arrangement would be, uh, yes, regular arrangement. Tightly packed with regular arrangement. But regular we won't use until unless we are sure that we're talking about a metal. So tightly packed should do the job for us, right? Now the separation. That is what if you remember, I asked you to memorize that tightly packed, but you have to add the other part to get the full score. Fixed positions, right? That is the arrangement for solids. For liquids, they don't have fixed positions, but they're still very close to one another, right? So tightly packed in fixed positions. Okay, separation or touching, right? Either way, touching each other, close to each other, right? Okay, perfect. Element X is in group 1 metal. It burns in air to form an oxide X2O. Write the chemical equation for this reaction. Now keep in mind you have to use the symbol X for it. Chemical equation. No, 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 no. They're not giving you any metal. They're saying X. You have to use X. X is solid, right? Reacts with O2, which is gas, gives you X2O. And that's going to be a solid, right? Because it's an oxide. Oxides are solid, right? They're ionic compounds. So ionic are going to be solid at room temperature. Remember the standard forms of every, right? Ionic compounds are in standard form. They are solids, right? Okay. And then we have to balance this. So that's going to be a 4 and that's going to be a 2 over here. So if you don't balance this, you don't get the score. Clarified? So remember, you have to use the same X because they're not telling us which metal. So we can't write Na over here. Okay. Next one. There you go. Magnesium and calcium and strontium are group 2 elements. Okay, group 2. Complete the table to show the arrangement of electrons in calcium atom. In calcium. How many electrons in the first one? Next. 8, 8, 2. Perfect. Correct. Okay, describe how the arrangement of electrons in strontium atom is. Strontium. Arrangement of atom. Tightly packed. In again fixed positions. And now, since we know that this is a metal or an ionic compound, right? Either way, what we say, fixed position with with regular arrangement. Very good, right? Now we're going to use the word regular arrangement with regular arrangement because we have to identify that these are crystalline in nature, right? I told you that metals are crystalline in nature. Okay, different from the arrangement of electrons in calcium atom. What's the difference? Loosely packed. Okay, just a minute. I need to complete because we're doing comparison, so we have to write same as calcium, right? Okay, different from arrangement of electrons in calcium atom. What is the difference? Mm-mm. Arrangement of electrons, dear. It's still a metal. It's strontium. What would be the difference in electrons? Yes. So it's magnesium, calcium, strontium, right? So we're going down the group. So what else is going to happen? No, an extra shell in terms of electrons, right? And more electrons, obviously. But the outer arrangement is going to be the same. So we cannot talk about outer arrangement, right? We'll have uh, extra shell and more total electrons, right? We're going to say total, not outer. Don't use the word outer here or you lose the marks all the way around, right? Because the outer is going to be same, right? 2, 8, 8, 18, and then 2, if you reckon, right? That's the arrangement for strontium, right? So, and more electrons, or you can say how many more electrons? 18 more electrons, right? 18 more, you can say, just to make sure that this is the arrangement, right? Clarified? We're just comparing it. Okay. Next, calcium reacts with cold water to form two products: a colorless gas P, which pops with the lighted splint. Pop with a lighted splint? No, pop. That is hydrogen. Very good. Okay. A weakly alkaline solution. Alkaline means it's a base, right? Solution, which turns milky when carbon dioxide is added through it. That's the CO2 test for us, right? And what would that would be? Calcium? No, hydroxide. Hydroxide, right? So name the gas. Again, it says no, no, no. Name. So you can't write H2. Hydrogen gas, you have to write, right? Complete word. Identify the ion present for making solution alkaline. Which ion makes the solution alkaline? It's not going to be calcium, right? Which makes something a base. Let's say I have anything X hydroxide. What once I dissolve it in water, which part dissociates and tells me that it's a base? It's the OH, right? H makes it acidic, OH makes it this. So we're going to say OH negative over here, right? Or you can say hydroxide ion. Now, since they use the word identify, so you can use either of them, right? You can write the name or you can write the ion. It's fine. Suggest the pH of solution Q. Now, pay very keen attention to this word, weakly, right? So how would you define a weak pH? No, that's strong pH, dear. That's the other end of the strongest here. From one strongest acid, yes, from 9 to 10, you can say. Okay, either way, just give them a range so that they can know that it could be somewhere between them, or 8 to 10 somewhere, right? 8 is also weak, but it says weakly alkaline, not extremely weak, so we'll still go with 9 to 10, right? Write a chemical equation for the reaction of calcium with cold water. So that's going to be calcium solid, cold water, H2O liquid, gives you, now it told you what the reaction is, right? They've already told you here, so you don't have to worry, right? It's going to form two products. One, it's going to form H2 plus, the other is going to be, yes, calcium OH whole twice, calcium hydroxide here, right? Right? Alkaline solution would be a base, and that's the base for you, hydroxide. Okay, which they're telling you the second product is alkaline and makes milky, and that I told you is this, right? You add this to this, you get calcium carbonate, right? And that makes it milky. Okay, this is not soluble, this is solid, right? So this becomes like white particles in your solution. Clarified? Okay, next one. Magnesium reacts with chlorine to form magnesium chloride. Magnesium chloride is an ionic compound. Complete the diagram to show the electronic structure of the ions in magnesium chloride. Now they've told you how many are there, right? This is 2 chlorine, so MgCl2. So that's going to be -1, that's going to be -1, and that's going to be +2 for sure, right? I can see it from here because we need one of this and two of this, right? And secondly, we still need to, yes, no, why would it be shared? Yeah, donated. So there we go with the 8 electrons because it is for the magnesium. Mg is 12, so that's going to be 2, 8, and 2. This 2 is shared off. So we have to put one cross there, one cross there. So they haven't made the chlorine shells. Keep in mind, we still have to draw the chlorine ones, right? Those are also missing. There you go, right? One cross here, and then are going to be your circle ones, right? Make sure to use this correct notation for the electrons of chlorine and the X, right? The X is going to be from magnesium. Okay. Next, give 3 physical properties that are typical to ionic compounds. Strong or high? High, melting and boiling points. Very good. Number 1. Number 2. Physical. Keep in mind, we're talking about physical only, not chemical. That's one. Correct. Next, harder to separate. No, that would be from melting to boiling again. Hmm. No, no, strong is physical, but strong is not a complete statement here. You can say strong electrostatic force is the reason behind it, right? We can't talk about that. We're talking about physical behavior. Yes. But again, that's the underlying reason, strong electrostatic forces. But that's not it. High density as well, dear. If they're if they're so strongly bonded, then the particles are very close to one another, right? So they have high density. And strength, you were right, they are conductors in molten form. Yes, you can say, right? Conductors in molten form. That is acceptable, right? I would go high hardness, right? Hardness means you cannot scratch them easily, right? They're very strong, as you said, right? So we will rather say hardness. But you have added a much better point over here that they're conductors in molten form, so all three are acceptable. They're insulators in solid form, that is also there, right? You can also say this because that's still a physical property, right? Insulator in solid form, even though they're ionic in nature, right? So either one should be acceptable. Okay. Next, aqueous magnesium chloride is added to aqueous silver nitrate. A white precipitate forms. Write an ionic equation for this. Include state symbols. Right? So magnesium chloride, MgCl2, reacts with silver nitrate, which is AgNO3. Right? Gives you AgCl chloride and MgNO3, right? But NO3 is gonna be whole twice, right? And Cl is gonna be one because it's Ag plus one, right? In your course. Okay. So first, yes, we have to balance, and secondly, the states. So magnesium chloride is soluble, aqueous. This is aqueous, very good. Solid, yes, it's a precipitate, and nitrates are all soluble, right? They're all soluble. Every nitrate is soluble, right? So that's going to be aqueous. So that's the precipitate, right? Okay, let's balance this. Nitrate, we need two of the nitrates, and I think putting a two here balances this, right? Okay, moving on. Sulfur is an important element. Explain how burning fossil fuels containing sulfur leads to formation of acid rain. Hmm. Hmm. Yes, it can. Why not? And most of them, keep in mind, these explosive materials, solid explosives that are being used right now for the Iran war, they have solid fuel, right? They do contain sulfuric compounds in them. So yeah, acid rains are going to be there, right? Massively. That is why it's random rain going on. I mean, right now it's raining in my, like, right outside for me. Okay, so that is due to the high thermal changes that are due to the missiles and whatnot, right? Obviously, that's a highly exothermic process. So yeah, the rains are going to happen, right? Out of the ordinary, right? Because we need temperature changes that causes condensation and fuel burning like through the air. So you do know that they use those salt flares to cause prosthetic rains, right? So it is like salt flares going all over the place, right? Because of so many, explosive materials being burned. So yeah, you're right. Okay. Yeah, but we have to narrate the answer based paper based answer, right? So how are we gonna narrate this? Hmm. No, we'll start with burning sulfur in air forms Now, sulfur dioxide, which when rains forms sulfuric acid. Yeah, dissolvent, right? It is an acidic oxide, right? It is an acidic oxide already, right? Forms sulfuric acid, which means acidic rain. Okay, so you can explain it like this. So remember, they're saying burning, so they are told you what to talk about, right? Already in the paper, that we have to describe it through burning. So burning sulfur produces sulfur dioxide, right? And that would be the problem, right? So we have S plus O2 giving you SO2, right? That's burning of sulfur. And this is exactly what we do in the contact process. We burn sulfur entirely. Okay, sulfuric acid is manufactured by contact process. One step in the contact process involves a reversible reaction. And I told you the only reversible reaction is with the SO3 one, right? Where you convert SO2 into SO3, right? And to balance this, we get two of this and two of this, I guess, right? Uh, yeah, balanced, right? So write the chemical equation of the reversible reaction with the symbols on it. So SO2 plus O2, this, and 2SO3, right? And all of these are going to be gases. Very good, right? These are gases. Perfect. So balancing. State the conditions for and then catalyst used for the contact process. Now keep in mind they're talking about the contact process. Temperature 4450 degrees, right? Next. Now that is for ammonia. This one is low pressure. But what's the value? 2 atm, right? That is for ammonia, my dear. For NH3 and 2 ATM. I just told you there's a difference of 100 and with H2SO4. And why is that so? Because this process already has a very high yield. We don't need high pressure problem here, right? And catalyst, vanadium oxide, V2O5, right? So vanadium, right? And we call it 5 oxide, right? Clarified? Vanadium 5 oxide, because that's going to be uh, minus 10 and that's going to be plus 2 to make it plus 10. Okay, describe how the sulfur trioxide formed is converted into sulfuric acid in the next steps of contact process. Next steps, not one, but multiple steps you have to talk about. Dissolved in concentrated, no, not oleum, right? That is H2S2O7, right? Which is further diluted with water. Yes, with water to H2SO4. Perfect, right? Okay. Next, dilute sulfuric acid. My dear, concentrated sulfuric acid is basically very high concentration of sulfuric acid, very little amount of water. Now, keep in mind, if you remember, I told you that all the acids in their native form are supposed to be pretty much very evaporative, and we don't call them as acids, right? If they're pure, 100% pure, are not called acid. Acid is the one which is including water in it, right? So concentrated would mean this is the difference, right? It would be liquid, but it should not be liquid. It should actually form at a gas version if you make 100% pure of it. But you don't get this, right? Very hard to get, right? This is what you really get even from here. So that is very high purity, but still it is dilute, right? So acids are water based, right? Pure ones are not called acids. Clarified? Okay. Uh, Next one. Dilute sulfuric acid is used to make salts known as sulfates. A method consisting of three steps is used to make zinc sulfate from zinc carbonate. right? Add an excess zinc carbonate 20 centimeter cube of this much dilute sulfuric acid until the reaction is complete. Filter the mixture, heat the filtrate until saturated solution forms, and then allow it to crystallize, right? Name a suitable piece of apparatus for measuring 20 centimeter cube of dilute sulfuric acid. Step 1. Yes. Measuring cylinder. Okay, good. Next, state two observations which would show that the reaction is complete in step 1. How would you know that? Hmm. No, in this case, this since this is a carbonate, so no more fizzing, right? No more fizzing or effervescence. That's one. Number two, a solid is formed. No, we will get zinc sulfate, which is soluble, right? Zinc sulfate is soluble. Plus, the other thing is CO2 going out and H2O. So there is no solid in this reaction. Let me just give the reaction, right? So ZnCO3 reacts with H2SO4, right? This is what we're doing. So we get H2O because it's a neutralization reaction, but since it's with carbonate, we get carbon dioxide and ZnSO4. So nothing is solid over here, right? So no. But remember, this is neutralization, right? Carbonates are weak bases, right? And that's an acid. Acid-based reactions are called. But what is how neutralization reaction? What is the key factor of neutralization reaction? Their delta H is always negative. They are hot reactions, right? They get very hot. So no more temperature increase, you can say, right? No more temperature increase. That shows that it is increasing, right? So you can say no more temperature change is correct, but if you say no more temperature increase, that will make the examiner feel very happy because he'll know that you know it is an exothermic reaction, right? So keep in mind these are exothermic reactions. Okay, so increase would give you a better chance of communicating with the invigilator, or sorry, the examiner, right? Why is it important to add excess of zinc carbonate in step 1? What? To ensure all of acid is used up, right? That's why, because we do know that the carbonates are insoluble, so we can easily separate them. That's why we're filtering it to separate the excess uh, carbonate, right? You get the idea? So, but we cannot separate excess acid if any left, right? So to make sure that there is no more acid left, we will have to add more salt in there, right? So that all the acid is used up and any unleft carbonate, we can simply filter it out, right? Since they're telling you that there is filtration step, so we can remove the solid particles. But what we cannot remove is like soluble acids, right? Because it would be liquid, it will go through the filter. So how would you know that all of the reactants have completely reacted, right? So for that we will add uh, excess zinc carbonate to ensure that all the acids is used up. Okay, what is meant by the term saturated solution in step 3? Oh, this I want you to define. Saturated solution. Mm-hmm. Mm-hmm. Now that contains that contains dash amount of solute. Maximum. Very good, right? You get the idea? You know the answers, except you're missing one or two words, right? Maximum solute possible, we'll say, at given temperature. Uh, RTP. Not necessarily, it could be at higher temperature as well. I mean, it's the same thing, right? So you can say any given temperature or any particular temperature, right? Either way it works. So maximum amount of solute, right, is your answer. Clarified? At any temperature, okay, or at a particular temperature. Okay, the equation for the reaction is shown. Zn CO2 this and this and this, right? what is going to be this over there? Complete the state symbol for zinc sulfate. Zinc sulfate is going to be, you can tell from here. This is already telling you. You're filtering it out. So the carbonate is filtered out. Obviously, yes, we're making a set. Yes, it is aqueous then, right? So it's going to be aqueous because we filtered out this. This is where filtering. So obviously, this is water. This is gone into the air. Obviously, this has to be the filtrate. Clarified? This is going to be your residue. In case if they ask you what is the residue, this is your residue, right? Which we got out of filtration. Okay. Next, name another zinc compound which could be used to make zinc sulfate from dilute sulfuric acid. What other compound can we use for the same reaction instead of zinc carbonate? Zinc oxide. Oh, name, sorry, right? Zinc oxide, right? Or you can also use zinc zide hydroxide. Very well. Okay, nice. Suggest why this method would not work to make barium sulfate from barium carbonate. Barium sulfate is insoluble from barium carbonate. Huh? Okay. Barium sulfate is insoluble. Okay. Uh, very right. Yes, yes, yes. Barium sulfate. Sorry, my bad. Right. Barium sulfate is insoluble. Okay. You said insoluble, right? Okay. Next. Why would that be? Because here's the problem. Because we want two stuff to be taken out, right? In this case, since barium sulfate is going to be insoluble and this would be insoluble, so filter will catch both of them, so will not get anything out, so they'll both be staying fixed up, right? So your excess and your product will both be stuck as residue, right? They will both be stuck as residue on filter paper. So still they are not separated. So hence this process you can make, it's not that you cannot make barium sulfate, but you cannot use this method. Why this method? Because the filtration will not work. Yes, you can use any other method for this, right? So it will precipitate out. That will be a trouble for us. It will mix up with barium carbonate and then we cannot separate it out, right? Okay, good, very good. Okay, in titration a student adds 25 centimeter cube of this. This is the concentration of aqueous sodium hydroxide to a conical flask. That the student adds few drops of methyl orange, right, to the solution. What would be the color of methyl orange here? Yes, sodium hydroxide should be. It is orange in acid, right? It is colorless in base, right? So it's a hydroxide, so it would be colorless, right? It gives orangish color or yellowish color in acid, right? Okay, determine brown. Let me check. Let me check. Maybe, maybe, maybe. No, no, no. That was for bromine. If I reckon acid basal salts, it would be here somewhere. The chart. Methyl orange. Oh, it is orange in base and pink in this. My bad. Right. So yeah, you're right. You're right. You're right. It would be pink. It would be orange here. So not colorless, but orange. As said, you'll have to memorize, my dear. I have a bad memory now, right? I'm too old. I'm getting too old. No, you basically you just have two of them to remember, and methyl orange is the one that you must remember the most, right? Methyl orange and phenolphthalein. I told you two of them. You just need to remember two of them. That's it, right? In acid and in base. I think phenolphthalein is colorless in base and something in acid, if I reckon, right? Okay. Determine the concentration of the dilute sulfuric acid. Calculate the number of moles of aqueous sodium hydroxide. In this, we have the volume, we have the concentration. So N is equal to CV, right? N is equal to, we have to convert the volume into dm cube. So that's going to be 0.025, right? 0.2. Yes. So how many moles? 0.005. Okay. calculate the number of moles of sulfuric acid in the period, because this is complete reaction, right? So they added this to neutralize completely. So how much is needed? It is 2 ratio 1, right? So it is 2 ratio 1. Hmm. It would divide by 2, so that would be 0.025. Perfect. Next, calculate the concentration of sulfuric acid in mole per dm cube. How much of the acid did we use? 20 centimeter cube, right? That's the volume. So N is equal to CV, yeah. C is equal to N by V, and 0.0025 divided by 0.02. Yes. How much? Perfect. Okay. Calculate the concentration in grams per dm cube. Grams. You have the moles though. Can you get the grams? Yes, we have to get the MR of sulfuric acid, right? That is 98. Okay. So we have the moles. So let's get the mass, because we have to get the grams. We need to get the grams first, right? That means we have to calculate the mass here, right? So the mass is going to be N into MR, right? And that's going to be 0.0025 multiplied by 98. That many grams are there. Yes. How many grams are there? 0.0025 multiplied by 98. That many grams. Now keep in mind, that is per dm cube we have to calculate. They gave us the volume, so we have to use now the concentration in mass per volume, right? So the mass is 0.245 grams, and uh, no, not 24. No, 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 that's for gases. No, no, this volume. We have to calculate for this much volume, right? So that's going to be 0.02. Keep the same volume, by the way. 1.225, right? Okay, 1.23 we have to write the answer, so I'm just going to write 1.2, right? Two significant values again, right? So 1.225. Okay. Physics and forces too much of the significant values. Okay, this one. Fe2SO4 decomposes when heated strongly. We have this decomposition. 15 grams of this was heated to form this much of FeSO4. Calculate the percentage yield. First, we need to calculate the theoretical yield, right? Theoretical. Theoretical means using the formula and the given value, regardless of this, right? So we have the MR and we have this for the MR. First, we need to see how many moles are there for the FeSO4, right? So first we calculate moles of FeSO4, right? That's going to be M over MR. We have the mass, which is 15.20, divided by the MR, which is 152 grams. So how much is it? 15.2 divided by 152. That's going to be zero point 0.1 mole. Yeah. Okay. And now you can see it is ratio 2 ratio 1, right? Since this is 2 ratio 1, how many moles are going to be there? 0.05 mole of Fe2O3. Now we have the moles. Let's take the mass out of it, right? So M, right? N is equal to M over MR. We have the N and the MR, so we can get the M out of it, and that's gonna be how much? 0.05. Okay, let me write it completely because Mirab is not here, so that she gets it when we once we're done, right? So that's going to be 0.05 multiplied by the MR, which is 160. So how many grams should be produced? 0.05 into 160. 8 grams. 8 grams, right? So that means 8 grams should have been produced, right? That is theoretical value. But we need to find the yield, which is like actual. They're telling you how much did got produced. This is actual, right? So now we take that percentage yield is equal. Let me use a different color, right? Percentage yield is equal to actual over theoretical, right? Into 100%. So that's going to be 4.8 divided by 8 into 100%, right? So forget about the percent. Just do this. 4.8 divided by 8 into 100. That should be around somewhat 6 something, point 0.6, 60%. Yeah, 4.8 divided by 8. Yeah, zero point 0.6. So 60% is the yield. Done? Yes, Nanya? Done here? Okay. Moving on. A student investigates the process of the reaction between dilute hydrochloric acid, HCl, and an excess large pieces of marble, right? Large pieces of marble. So I'm going to highlight this on calcium carbonate, right? Limestone, we call it. And dilute hydrochloric acid, right? Using the apparatus shown. This is the dilute, and this is this, and then we have a syringe. Okay, a graph shows the volume of the gas produced against time is shown. That's the graph, right? From the graph, we can tell how much is the. How does the shape of the graph show that the rate of reaction decreases as the reaction progressed? Yes. How can the shape tell you? It goes straight? No. The better way is gradient of graph decreases as it progresses. We're not going to talk about stopping right now because they're saying progressed, not that when it got completed. At this point, it is completed. So flat line is completion. Keep in mind. So we're not. They're not asking for completion. They're asking for progress. Right. This is the progress part. So we're going to talk about the gradient only. Why did the rate of reaction decrease as the progress as the reaction progressed? Less particles with activation energy left, right? You get the idea. There are lesser particles with activation energy left in uh, reaction vessel, whatever, right? Or in conical flaws. Okay, there are lesser particles left with activation energy. Okay, after how many seconds did the reaction finish? How many seconds? 120, right? 120 seconds. The experiment was repeated using the same mass but smaller pieces. Yeah, I was wondering that they're going to put something like this, right? All other conditions were kept the same. Draw on the graph to show the progress of reaction using smaller pieces of marble. Inclined, right? So it will go something like this. Initial reaction would be fast and it will complete a little bit earlier, like this, right? Perfect. That's going to be same. Do not, I see a lot of kids making it higher. It cannot be higher because the rest of the conditions are same. So the total amount of gas produced would be the same, right? It's just the faster rate. Okay. The original experiment was repeated at higher temperature. All other conditions were kept the same. Describe and explain in terms of collision between particles. Now, collision between particles, right? Collision. We have to use these words. The effect of using higher temperature on the time taken for the reaction to finish. Yes, how would you rate this? For 5 marks. With higher temperature, yes, particles will have more kinetic energy. Hence, they will collide more frequently. Very good. Very good. This will increase the possibility of more successful collisions as a result. Yes. Less time taken to complete the reaction. Perfect. Very good. Right? Exactly. Great. Okay. Next, alkynes. Last question, I think. Right? Alkynes are homologous series of unsaturated hydrocarbons. Right? Again, alkynes were not in your group, but it's the same idea. Right? Name these. This is ethine. This is three carbon. So ine is gonna be the same. What's gonna be the first part? How many carbons are there? Three. So what would you call it? Pro Propine. Very good, right? It's just going to be the pro. Iron is the same thing. And over here, this is butane. So the formula should be C4. You can count, right? Right? Six. Okay. The formula for ethyne triple bond is basically CN H2N minus 2, right? It's like 2 less than the ethane. But again, this is no more in your course, right? So again, it's a 2018 paper. Okay, next, complete the dot and cross model for this. It's a triple bond, keep in mind. So we have to make how many dot and cross in there? Three of them. So one, right? Two, three, right? So I'm going to take dot for one and the cross for the other. And the hydrogen is just going to be dots and one cross, right? So this is how it's going to make. Clarified? Okay. Again, it's very difficult to narrate the dot and cross model. Okay, compounds in the same homologous series have the same general formula. Give two other characteristics of the members of homologous series. They have the same functional group. Very good, right? Functional group and similar chemical properties. We cannot say the same for physical properties, right? Because they change due to their masses, right? They have same chemical properties. Very good. Okay. Perfect. Next, use the information in the table in A to deduce the general formula of alkynes. I just did that, right? Since it would be not for you, alkynes were as said before, so I'm just gonna write it, right? That's gonna minus two. Alkynes are unsaturated. Just consider as alkenes, okay? Are unsaturated. Describe it as for unsaturation. Unsaturated hydrocarbons. Sorry, testing with? No, no. What would it do with water? Nothing. It won't even dissolve in water. Bromine water test, right? And what happens? What's the result? It will decolorize bromine water, right? Or it will change it to colorless, right? Either way, you can express this. Okay. Next, name an oxidizing agent which can be used to oxidize ethanol to ethanoic acid. Ethanol to ethanoic acid, oxidizing agent. Ethanol, fermenting, oxidizing agent, dear. What oxidizing agent can we use? In other words, the catalyst that they're using, surprisingly, here, right? Potassium permanganate? No, that's not for the ethanoic acid. Is that so? Okay. I think sodium hydroxide we can use for this. We need hydroxide. Potassium permanganate, right? Right? Yeah, KMNO4. Okay, we'll see. Right? Draw the structure of ethanoic acid. Uh, Show all atoms and all bonds. Right? It's a displayed structure. Ethanoic acid. Perfect. Okay. Carboxylic acids can be converted into esters. The ester formed by reacting propanoic acid, right, has and methanol has a molecular formula of this methanol C1, right? Name the ester and draw its structure. Name the ester. They gave you the very good, right? Methyl propanoate. Okay, and the structure. Hmm, right? This thing. This is the ester link in between, right? Okay. Name another ester with molecular formula this. Any other ester. Very good. Right? Ethyl ethanoate. Another one which you can name. Perfect. Very good. Right? Propyl methanoate. So we can do two of them, right? Either one of them. Perfect. Polyesters are polymers. Polyesters, right? What type of a polymerization is used in manufacturing of polyesters? Now, condensation, right? I told you only double bonds or alkenes can do addition polymerization, not the others. Others do condensation polymerization, right? Name an polyester pet. I told you you have to memorize this one example for this. And for polyamide, we have nylon, right? Okay. Is it end? I think that's the end of the paper. Yeah, that's the end of the paper. Okay. All right. So this was good paper for you. Very good. Good collaboration here, right? So you've improved quite a lot, right? I'll give you we'll do one more P4 tomorrow, right? And then I'll share the oh dear, am I recording this?